Thank you all for being here and participating in the today's SISSA IFPU webinar on gravity. Today we have with us Nico Sanchis-Gual. So Nico is currently a postdoc research at the University of Aveiro and a member of the LIGO-Virgo collaboration. During the last years, he has been dedicated to the study of the dynamics and the gravitational wave signals emitted by astrophysical compact objects, either black hole or neutron star, and exotic theoretical compact objects like boson star or scalarized black holes. He got his PhD in physics from the University of Valencia in Spain under the supervision of Professor Tony Font. Afterward, he moved to the Center for Astrophysics and Gravitation in Lisbon, and since September of the last year, he has been working at Aveiro University in Portugal with Carlos Herdeiro. So today he will talk about Light in the Dark, GW 190521 as a Proca star major. Oh, go ahead, Nico.
Okay, so hi everyone. Thank you very much, Miguel, for your nice presentation. And thank you very much for inviting me to give this seminar and present some of my recent results. So my name is Nico Sanchis-Gual. I'm currently a postdoc at the Graph Group in Aveiro. And I'm going to talk about Light in the Dark, GW 190521 as a Proca star merger. This work has been done in collaboration with Juan Calderón Bustillo, Alex Torres Forné, Tony Font, Carlos Herdeiro, and collaborators, and was recently accepted for publication in PRL. So actually, I will talk about GW 190521 and the Proca interpretation at the end of my talk. We'll first give a brief review on some of my results on bosonic stars and bosonic fields. So let me first try to motivate the study of bosonic fields and bosonic stars as exotic compact objects. So as you know, the detection of gravitational waves by LIGO-Virgo and SUM-CAGRA are opening up a new window into the strong field regime of gravity. However, even though the data so far is well fitted by the expected physics, this is Kerr black holes and neutron stars, it is important to understand if alternative non-conventional models of exotic compact objects can also fit the data, or how much this can be ruled out by current or future detections. So obtaining gravitational waveforms from these exotic compact objects could lead to their discovery if they indeed exist in nature, or at least lead to a degeneracy in the observed emitted gravitational wave. So here I show the stellar graveyard from the second release of the gravitational wave catalog by the LIGO-Virgo and CAGRA collaboration. And we have around 50 gravitational wave events so far. And all of them can be explained by mergers of Kerr black holes, neutron stars, or even a Kerr black hole with a neutron star. But actually no one has tried to fit with an alternative model of an exotic compact object these signals and see if they fit better the data, or at least there is this degeneracy. So if we want to study exotic compact objects, in particular boson stars, we require general relativity, GR. So boson stars are described within GR. So we have to solve the Einstein equations numerically that play a fundamental role in the analysis of the dynamics of the gravitational field and can be coupled to the Klein-Gordon and the Proca equations, which govern the dynamics and the properties of the bosonic fields. So scalar boson stars and its vector cousins, known as Proca stars, are made of particles with integer spin that follows the Bose-Einstein statistics. So they are made of bosons. At the lowest energy level state, they can be classically described by a wave function, which is characterized by the particle mass mu, which plays a very important role in the description of the model. So if we consider a complex bosonic field with an harmonic dependence to evade stability theorems such as Derrick's theorem, we have a real and imaginary parts that are oscillating with the same amplitude and with the same frequency, but with a pi-half phase difference. Therefore, the amplitude of the complex field can remain constant with time. So while the field is oscillating with a determined frequency, the space-time is kept static or time-dependent. So even if the field is changing with time, it's oscillating with time, at the level of the stress energy tensor, it's time independent. So the space-time can be time independent. Therefore, the star can form a stationary, soliton-like, horizonless, everywhere regular solution of the Einstein complex massive Klein-Gordon system for scalar boson stars and of the Einstein complex Proca system for Proca stars. It is interesting to know that a real field can also form massive solitonic solutions known as oscillatons. But in this case, the stress energy tensor is not time independent and the space-time is no longer static. So the field will decay with time to infinity. But actually the time scale of this decay can be longer than the Hubble time, and therefore these objects could have astrophysical relevance if a real field existing, real bosonic field existing in nature. So in this short movie, I'm showing the time evolution of the real and imaginary parts for a bosonic star structured at some radius, the bosonic field, the amplitude, and you see how they oscillate with the same frequency, with the same amplitude, but with a pi-half phase difference. So the amplitude can remain constant with time. So for neutron stars and white dwarfs, we can identify the Pauli exclusion principle and the Fermi degeneracy pressure has the quantum mechanical principle that supports these objects against gravity. For boson stars, we can identify the Heisenberg uncertainty principle. So it's the tendency of the field to disperse that will balance the attraction of the field itself. And actually, in this very nice, review on dynamical boson stars, Liebling and Palenzuela managed to obtain an estimate of the maximum mass from the Heisenberg uncertainty principle for a non-spinning scalar boson star. And actually, their estimate is very close to the actual correct maximum mass that can only be obtained if we solve the fully nonlinear coupled Einstein Klein-Gordon system. And you can see that the maximum mass is just like for neutron stars. The maximum mass actually depends on the bosonic particle mass. So if we want to have a maximum mass in the range in which LIGO and Virgo and Cagra can detect mergers of these objects, so between one solar mass and thousands of solar masses, then the particle has to be ultralight, having a mass around 10 to the minus 10 electron volts and 10 to the minus 14 electron volts. We can also study the shadow of these objects and compare them to the shadow of a black hole and compare it with the image obtained, for example, with the Event Horizon Telescope. And actually, in our group, Pedro Cunha, Carlos Herdeiro, and Eugene Radu are experts in obtaining the shadows of these exotic compact objects, these bosonic stars or other type of objects such as Kerr black holes with bosonic hair, or even scalarized black holes in models beyond GR. So in a cosmological context, even scalar fields have been proposed as constituents of dark matter halos in galaxies. So you have an ultralight bosonic field with a mass between 10 to the minus 22 and 10 to the minus 24 electron volts. The Compton wavelength is of the order of the radius of dark matter halos in galaxies of kiloparsecs. But are black holes a threat to the scalar field dark matter models? Well, it has been shown that black holes can develop quasi-bound scalar field or Proca field configurations that may be very long-lived, depending on the mass of the particle, of the bosonic particle. Moreover, recently it was shown by Carlos and Eugene that astrophysical rotating black holes described by the Kerr metric could have scalar or Proca hair. So we have a bosonic field that is around a rotating black hole, and actually they are both, it's an equilibrium configuration, it's an stationary solution. So I think that it is becoming increasingly clear that scalar fields or even vector fields could have a tremendous impact in many areas of astrophysics, or even in theoretical physics, in high energy physics and particle physics, becoming a link between these different fields. So numerical studies can be undertaken in order to make predictions and understand the properties and the dynamics of bosonic matter. Because bosonic matter has a very rich and interesting phenomenology. For example, it can trigger the supernova instability around rotating black holes and form hairy black holes. So as you know, black holes have no hair. This means that they are well described by the Kerr-Newman family. So they are characterized by their mass, angular momentum, and electric charge. But in 2014, Carlos Herdeiro and Eugene Radu found asymptotically flat stationary solutions in GR of the Einstein complex massive Klein-Gordon and of the Einstein complex Proca systems that they call Kerr black holes with bosonic hair. Here we have this bosonic field around a rotating black hole, which is synchronized. It has also angular momentum, and it's synchronized with the horizon velocity of the black hole. So the system is in equilibrium. It's a stationary time-independent solution. So bosonic fields can also trigger the superinstability around rotating black holes. It has been called the black hole bomb, this system. And actually, this means that an incident wave of bosonic field that is scattered off a rotating black hole, the reflected wave, the amplitude of the reflected wave can be larger than the amplitude of the incident wave, because the bosonic field will extract energy and angular momentum from the black hole, spinning it down. So if we are able to trap this super-energy scattered wave by considering a massive bosonic field, so the potential well due to the mass term will trap the bosonic field, then we can, or put in a cavity with reflecting boundary conditions, then we can trigger the black hole bomb. But the study of the endpoint has been an open issue since the 70s, because numerical relativity simulations were mandatory to study the nonlinear regime. However, the time scale of the superinstability for a scalar field around a rotating black hole is too long to be performed with current computational capabilities. But actually, there is a more favorable situation, which is considering a charged black hole, so a Raysen-Nostrom black hole, which can be studied in spherical symmetry. So we put this black hole inside a box, inside a cavity, and we perturb it with a small perturbation of a charged scalar field. Then we can trigger an analog system, the charged black hole bomb, that can be studied using numerical relativity. So we have to solve the Einstein-Maxwell charge complex Klein-Gordon system. And that's what we did. And actually, at the same time, the group of Louis Lehner did it, but in asymptotically anti-de Sitter, so not considering a cavity. And what we saw the same features. We saw a first phase of superradiant growth, in which the bosonic field is extracting charge and energy from the black hole and growing its own energy and charge exponentially. But then there's some point at which there is a saturation and we reach an equilibrium configuration, which corresponds to the formation of a charged hairy black hole. And actually, it's related to the condition of the superinstability. So in this case, there is an equilibrium between the oscillation frequency of the field and the electric potential of the black hole at the horizon. Here I show a simulation of the energy density of the scalar field. So it's trapped inside the cavity. You see that it is growing with time, extracting energy, but at some point we reach the equilibrium and we form a charged hairy black hole. So it seems that the endpoint of the charged black hole bomb is a charged hairy black hole. But what happens in the rotating case, the more interesting case, because it's astrophysically relevant? Well, William East and Pretorius in 2017 managed to study the endpoint of the rotating black hole bomb, but not for a scalar field, for a Proca field, a vector field, because the time scales are orders of magnitude shorter than for the scalar case. And basically they found the same features. They found the exponentially growing phase, which the field is extracting angular momentum and energy from the black hole. But at some point there is this saturation and it reaches the equilibrium configuration, which is a hairy black hole. And actually, Carlos Herdeiro and compare the configurations that they found before this simulation, and they found that indeed they were the same that East and Pretorius were obtaining from the numerical simulations. So the endpoint of the superinstability in the rotating case is a hairy black hole, a Kerr black hole with bosonic hair. So, okay, so also I think it's important to mention that a real field can also, this is for a complex bosonic field, but for a real field can also trigger the super instability around a rotating black hole, but the endpoint is not an equilibrium configuration, a stationary configuration. Instead, the stress energy tensor is not time independent, so the system will emit gravitational waves. And actually this gravitational and the cloud will decay with time through the emission of these gravitational waves. And actually we can search for these continuous gravitational waves, and that can be detected or not if there is no such bosonic field. And we can constrain the masses of these ultralight real bosonic fields. Okay, now let's move on to objects that do not have an horizon. So let's describe the spherical non-spinning boson and Proca stars. So the scalar boson stars have been known since the 70s, have been extensively studied both analytically and numerically. But Proca stars have only been obtained as solutions of the Einstein complex Proca system very recently in 2016 by Brito, Vitor Cardoso, Carlos Herdeiro, and collaborators. And they resemble the Proca stars, resemble in many ways their scalar cousins, the scalar boson stars. You can see here the Proca field Landsat. It has this harmonic dependence. So we have a complex field, but then it's a vector field. And it's very similar to the scalar field Landsat. So if we build the sequence of equilibrium configurations, of equilibrium solutions in spherical symmetry, we get that Proca stars have this maximum mass model, just like for scalar boson stars, slightly larger the mass, the maximum mass. But then we have this branch of models that are stable against linear perturbations, and then the branch which is unstable against these perturbations. So this is actually like for neutron stars, for which we have also a maximum mass, stable branch, and unstable branch. So for bosonic stars, we can also put a self-interacting potential like phi to the 4, for example. And we have this parameter lambda that we can increase, and we see that the maximum mass for the same mu, the same particle mass, just increasing by increasing the self-interaction. So if we study the stability of isolated non-spinning spherically symmetric bosonic stars, we see different outcomes. So the models in the stable branch are stable, even if we perturb them. But the models in the unstable branch can have different fates, different outcomes. So depending on the sign of the binding energy, and depending if we add or not a perturbation. So we have models that have an excess of energy, so they are not bounded, so they just disperse to infinity. If we add a sufficiently large perturbation, these stars can collapse and form a Schwarzschild black hole. So we see that outside of the black hole, there is, for some models, there's a remnant of bosonic field that form these quasi-bound configurations around the black holes that are decaying exponentially. So the black hole this bosonic field is falling into the black hole with time. And we can have also models that migrate to from the unstable branch to an unstable configuration. So actually, they become less compact, and they start to oscillate around this new configuration. And in 1994, Seidel and Suen found that they could form dynamically these scalar boson stars through a mechanism that they call gravitational cooling. So basically, they started with a dilute cloud of a spherically symmetric dilute cloud of scalar field, described by a Gaussian distribution. So they let it evolve, and they saw it's not compact enough to collapse to a black hole, but instead it collapsed and formed at the center of the computational grid a compact object that resembled very much to a scalar boson star with the same parameters, with the same oscillation frequency and mass. So in 2018, we repeated the same scenario, but now with a Proca field. So we start here with a dilute cloud, spherically symmetric dilute cloud of Proca field so we start the evolution, and we see that it collapses towards the center of our computational grid, and then it forms something in this region that is a compact object that is actually a perturb. And we see here the gravitational cooling that it just radiates away the excess of energy. So if we look at the energy density profile, we see that our newly formed Proca star is actually a perturbed one, which is oscillating radially around the Proca star solution with the same parameters of mass and oscillation frequency. And something to note is that for Proca star, the less compact models have the maximum, which is not at the center, at the origin, like for scalar boson stars, but it's a bit away. So it's like a spherical shell of matter. Okay, so I have discussed the stability of non-spinning spherically symmetric bosonic stars. Let's move on to the more interesting case of spinning bosonic stars, bosonic stars with angular momentum. So now the Proca field and the scalar field answer is a bit more complicated, and we have here this M, which is the azimuthal number, or the number of maximum. It's like the angular momentum in the equatorial plane. So it's the number of maximums maximums in the equatorial plane of the field. So for m equals 0, we recover the non-spinning scalar boson stars and Proca stars. For m equal 1, we have already these models with angular momentum. So actually, there's nothing in between these models. So the angular momentum is quantized. And Carlos and Eugene found models of an m equal 1, this is for Proca, an m equal 1 Proca in the nodeless, so in the fundamental branch, in the fundamental state, and then also models with a node, this curve, which corresponds to excited states. But actually, we can also find for higher m's, for m equal 2, m equal 3, m equal 4, etc. These models are also spinning Proca, spinning bosonic stars that will store even more angular momentum. Okay, so if you look at the energy density profile for m equal 1 Proca stars and for m equal 1 scalar boson stars, you see that there are differences. So you can see here that an m equal 1 Proca star has an spheroidal distribution, energy density distribution, for which the maximum of the energy density is at the center. On the other hand, an m equal 1 scalar boson star has this toroidal shape. So let's see if this different distribution has some effect on the stability properties. So what we did was first try to form these spinning Proca stars from the same scenario that Seidel and Suen studied for the formation of non-spinning scalar boson stars. So we start with a dilute cloud. This is for Proca, of a Proca field, but now with angular momentum. So this cloud has angular momentum. So we let it evolve, and we found that first it collapses. There is some emission of the excess of the field. It's a perturbed star, but at the end of the simulation, we still have something there that resembles actually a stationary solution of a spinning Proca star. So just like in the spherical case, we see that it's oscillating around the stationary solution with the same parameters, the same mass, the same angular momentum, and the same oscillation frequency. So let's repeat the same experiment, but now for a cloud scalar field with angular momentum. Let's see if we can form this spinning scalar boson star. So our cloud has this toroidal shape. So we evolve it, and we see that it collapses, gets something more compact, but at some point, there is this non-axisymmetric instability that kicks in and actually destroys the shape of the star, and decays onto something that is spherical and does not have angular momentum. I will repeat the simulation, see around 3,000 times, see that something kicks in, an axisymmetric perturbation that just destroys the star, which is the case to this spherical non-spinning solution. So, okay, maybe we cannot form through these gravitational coolings from the collapse of this cloud, but maybe spinning boson stars are stable. So let's try to evolve a stationary solution. So what we see is that at the beginning it stays there, but around time of 1,000, we see also this non-axisymmetric instability that destroys the star. And because this model is more compact than the cloud, it actually collapses and forms a Kerr black hole. So, okay, so it seems that we can form spinning Proca stars. So spinning scalar boson stars seem to be unstable, but we can form spinning Proca stars. Let's check if spinning Proca stars are really stable. So let's try to trigger a hidden non-axis instability by perturbing a stationary model by adding this type of non-axis symmetric perturbation, initial perturbation. But what we see is that very quickly it recovers its spherical shape, and the star, even if it's slightly perturbed, it stays there. And even if we can try to evolve an excited state, actually it's this number 3 with this node, so the energy density profile has two maximums, and we can see that it very quickly, it actually decays, it loses the node, the excess energy, and decays to the fundamental state. So this is for the Proca field, for the real and the imaginary part. You see that it loses the node. So it can even form from the decay of an excited state, these Proca stars. So to sum up, M=1 Proca stars, spinning Proca stars, can be formed dynamically from the collapse of this cloud with angular momentum. They are stable even against non-axisymmetric perturbations. But on the other hand, we have that M=1 scalar boson stars. We try to form them, they decay to the spherically symmetric boson stars without angular momentum. And actually this is in good agreement with the findings of Carlos Valenzuela and Miguel Bezares, when they try to, and collaborators, when they try to form rotating scalar boson stars from the mergers of non-spinning scalar boson star binaries. And they found that the final result, the final object, was either a black hole, a Kerr black hole, if the scalar boson stars were compact enough, or a spherically symmetric boson star, which radiates all the angular momentum. And we have, if the model is compact enough, then it will collapse to a black hole. Okay, so at first we thought that the instability could be related to the fact that, to the type of field, of bosonic field that we are evolving. Maybe Proca fields, maybe vector fields are more stable than scalar fields for some reason. Or maybe it could be related to the actual morphology, to the energy distribution of these two of the different stars. So maybe an spheroidal with the maximum, the peak of the energy density at the center is more stable against nonlinear perturbation, non-axisymmetric perturbation than a toroidal kind of energy distribution. Actually, there's a way to test this hypothesis. It's considered, that's why I've put here explicitly M=1. So an M=2 or even higher M's for both cases, and a higher M Proca star has a toroidal energy distribution. So we can see if an M=2 Proca star with this toroidal distribution is stable or also suffers this kind of instability. So we try to form these M=2 Proca stars, and we found that they are also prone to this non-axisymmetric instability. And actually they decay not to the non-spinning solution, but to the M=1. So at least for these configurations, the Proca field can keep part of the angular momentum, and it decays to a spinning solution which is stable. And actually, you can see here that the perturb, and during this kind of anti-merger, this splitting into two pieces of our star, there's this emission of gravitational waves. So we can also ask ourselves if we introduce some self-interaction potential, like phi to the 4, for example, if this kind of nonlinear interactions can quench the instability for these spinning bosonic stars. And actually, the answer is in principle no, because you can see here that we go from lambda = 60 to 300, and actually what we see is that the instability takes longer to kick in and to destroy the star. Even for lambda equal 300, we see that at the end of our simulation, there is no sign of the instability, but we expect that after some time, it will the star will decay to the non-spinning solution. So it seems that this potential cannot really quench the instability. So you can see here this time evolution of the mass and the angular momentum for some model, and you can see here when the instability starts, then the loss of angular momentum is larger than the loss of mass. And because the angular momentum is quantized for this model, this means that all the angular momentum will just be radiated away. And we get these kind of gravitational waves from these systems, and this can be seen as at the end you have some perturbed spherically symmetric non-spinning bosonic star that is emitting gravitational waves. You can see it has a continuous emission of gravitational waves, and actually we check that depending on the mass of the bosonic particles, going from 10 to the minus 11 to 10 to the minus 19, will change the mass of your object. And we check at which luminosity distance, depending on the type of the gravitational wave detectors. So here we have the ground base, LIGO-Virgo, the ET, then LISA, the space-based detectors, and then PTA, the pulsar timing array. So we could detect different types of bosonic fields. And I think it's really interesting to mention that actually this type of instability is present in neutron stars. It's a well-known instability. It's called the bar mode instability, in which also for quasi-toroidal neutron stars, you can have the m=2 mode of the instability that grows exponentially until it reaches the peak, and then it decays to something which is spheroidal, retaining part of the angular momentum in the case of neutron stars. But this is exactly what we saw for these spinning bosonic stars. Sorry. So we have the m=2. First, we have the m=4 that's dominating, but then we have the m=2 that dominates, reaches the point, and then it decays to the spherically symmetric non-spinning bosonic star. So actually, it's interesting to see that bosonic stars can also suffer this bar mode instability. So it could be that it's not a matter of, it actually doesn't depend on the matter that you are evolving, but more on the kind of energy, on the energy distribution of the object, of the compact object that you are studying. And also, I wanted to say that I've said that it seems that we found that the self-interaction potentials cannot quench the instability, but recently Simonsen and East found that for some range of the parameter space for this kind of 5 to the 4, but also axionic couplings, different type of nonlinear interactions for different self-interacting potentials for the scalar fields, they found that solutions of rotating scalar boson stars that are indeed stable, or at least they seem stable. They do not suffer the instability during the time of the evolution. So it could be that it seems that for even larger values of the lambda, of the parameter of the self-interaction, you can really get models that are stable and the instability would be quenched. So it could be that scalar spinning boson stars are back in the game if this is confirmed. Okay, so we have studied the stability and the formation of these bosonic stars with and without angular momentum. So let's put them in a more interesting, from the astrophysical point of view, scenario. So in binaries, to perform mergers, to compute the gravitational waveforms. And well, my goal is to build a gravitational catalog of these mergers of bosonic stars to then compare our results with the real gravitational wave events. So to see if we can really fit these signals. And I have to say that, well, Carlos Palenzuela, Luis Lehner, Liebling, Miguel Bezares, Paolo Pani, Vitor Cardoso, they have been working a lot on head-on collisions of boson stars, on orbital dynamics of binary boson star systems, also compact boson stars and gravitational wave signatures of compact boson star binaries. So I've focused on the collisions on mergers of Proca stars instead. So I started doing some head-on collisions of non-spinning Proca star models. And actually you can see here that, so this is more compact models. The less compact model can even not collapse after the collision. So what you get is a perturbed Proca star. But then you have models that collapse and form a Schwarzschild black hole. But it is interesting to know that there are models that are not compact enough to collapse right after the collision. So it forms like an hypermassive Proca star that is collapsing, but it's emitting gravitational waves. So we can compare these gravitational waves to the ones emitted by a head-on collision of two black holes with the same mass than the Proca stars. And we saw some differences in the ring down due to the presence of this remnant, this bosonic field remnant. And also we saw this difference. For example, you can see here that you have this extra signal coming from the fact that the star does not collapse right after the collision. So you have an extra part of the signal that is not present in the black hole collision. And it could help to differentiate these two systems. Okay, so the next step is to move to orbital mergers. So I started doing, so it's a superposition, and then we boost the solution with opposite directions. And this is for low velocities, low initial velocities. So it's not, they do not perform an orbit. It's not really an orbital kind of merger. It's more like an eccentric collision. But in this case, what we have is a Kerr black hole. So it's a black hole with angular momentum. And we see a remnant outside the black hole. So one may ask, can we form hairy black holes from these bosonic star mergers? So it depends. This is the oscillation frequency of the remnant. This is the horizon velocity. To form a hairy black hole, then the frequency has to match this quantity. This is the azimuthal number. So in the super-random case, we always study the m = 1 case because it's the time scales are shorter. But we need a highly spinning black hole, a 0.99 Kerr black hole, to get the hairy black hole, the synchronization condition. So it's really hard to obtain that kind of highly spinning black hole from the mergers of bosonic stars. But it turns out that the m is not equal to 1. What we get is that the remnant has a higher m. We get an m = 4, an m = 6, and even we found an m = 12. So actually the m = 12 is not a hairy black hole. These two solutions, this is for the scalar boson stars and these Proca stars, these are hairy black holes, but they require a fine-tuning of the initial velocity. But still, we can form this hairy black hole from these mergers. Okay, then the next step is, of course, performing quasi-circular orbits. This is work in progress, also because we do not have initial data, which is solution of the Einstein equations. It's just a superposition. There are constant violations, so we are working on getting this initial data to then perform these quasi-circular orbits. But we can also study mergers of spinning Proca stars, because these spinning scalar boson stars are unstable. So I started doing some head-on collisions of spinning Proca stars that collapse and form a black hole. We can compare them to head-on collisions of Kerr black holes. And we have models that do not collapse. And so the models of head-on collisions of spinning Proca stars that are not compact enough to collapse and form a black hole. So we do not have the ring down. Instead, we form a perturbed star that is emitting gravitational waves. So these last months, I've been working on performing a lot of simulations of head-on collision of spinning Proca stars to build this catalog of this type of scenarios. And actually, so I've tried to cover part of the parameter space. So this is the oscillation frequency that determines the compactness and the mass of the star. So from 0.8 to 0.93, so this is how the gravitational waveform changes as a function of omega, so as a function of the compactness, from more compact to less compact. Okay, so we have this catalog with well, it's for head-on collision of spinning Proca stars, but we still have this catalog. So can we try to feed these our waveforms to some of the real gravitational events? The problem is that almost all the events detected by LIGO and Virgo are similar to GW15 or 914, in the sense that it's a quasi-circular binary. So we have the inspiral part of the signal that comes from the quasi-circular inspiral. So the binary is losing angular momentum by emitting through the emission of gravitational waves. Then we have the plunge and the merger. So we have the peak of the emission and then the ring down. So this is the GW15 or 914 signal. It's a chirp type of signal in the sense that we have this inspiral part in which the amplitude and the frequency is growing with time. It's increasing with time. Then we get the maximum, like the chirp of a bird. So we cannot feed this type of signal with our short gravitational waveforms coming from the head-on collision of two spinning Proca stars. But then there is this special event, which is GW190521. It's the last individually reported event by the LIGO and Virgo collaboration before the second release of the GW catalog. And I say it's special because it's the most massive binary event ever detected. So the mass is 150 solar masses of the final black hole. So it's the first direct detection of an intermediate mass black hole. Sorry. So it's the most massive colliding individual black holes. But the thing is that the masses of these individual black holes are within the pair-instability supernova gap. So this challenge, what we know, challenge the models of stellar evolution. So this black hole shouldn't have these masses according to stellar evolution. So as you know, also probably is that they show GW190521 shows sign of precession in the sense that the spins of the individual black holes are not aligned with the orbital plane. Instead, they are not aligned. So there will be a modulation in the gravitational wave signal. So if you look at the spectrograms, you see that the signals is not similar to the first one, to a chirp type of signal. We do not see the chirp. We don't see really the part of the inspiral. It's just really the end, the peak. So it could be that due to the fact that this is really massive, the most massive event ever detected, it could be that it goes to, so the frequencies are lower than for example, for GW15 or 914. And actually, due to the sensitivity curve of the LIGO and Virgo detectors, there is this wall at low frequencies in which we cannot detect the gravitational wave due to the noise. So it could be that the inspiral part is just hidden behind this wall at low frequencies. But it could be that the signal is really short. There is no inspiral. It's not a quasi-circular. It's not a quasi-circular merger. It could be an eccentric collision. It could be even a head-on collision. So we started to study if precession could mimic with Juan Calderón Bustillo, Tony Font, and Alejandro Torres Fornés. We study if precession could mimic extreme eccentricity. So for precession, we have this modulation of the signal of the inspiral part. And actually, this is the red line is a head-on collision. So if we inject a head-on collision of two spinning black holes in some noise, and we try to recover it with precession, actually for large masses, they become indistinguishable. So eccentricity could mimic precession for really large masses. So let's see if GW190521 can be fitted by a head-on collision of two black holes. But actually here, so this is the Livingston data. You see that the green curve, it corresponds to the head-on collision of two black holes, but this is not enough to really fit the whole signal. We can fit the ring down, but we cannot fit the pre-merger, the pre-peak signal. So, okay, but maybe we have some matter star that do not collapse after the collision, but instead it collides and then it stays there and it starts to emit some extra gravitational wave, and then it collapses and we have the ring down. So what happens with the head-on collision of spinning Proca stars? So you can see here, maybe it's in spiral, or maybe due to the sensitivity curve, it's really a short signal. So if we perform a Bayesian inference analysis of GW190521 with these Proca stars. So Juan Calderón Bustillo was actually in the paper writing team of GW190521, so he's an expert in Bayesian analysis. And we find that we could recover the same parameters of the mass, the final mass in the source frame, and the final spin with Proca stars, but not with the head-on collision of Proca holes or black holes. The same, this mass and spin, than with the quasi-circular binary black hole interpretation. And actually we found that according to this Bayesian inference analysis, which is a standard Bayesian inference analysis, we found that our Proca star collision was slightly preferred, and even it fits slightly better this signal than the vanilla quasi-circular precessing black hole solution. Of course, this is not any strong evidence of the existence of Proca stars. We are not claiming that, but it's well, at least this is a degeneracy in the emitting sources. We can, even with this head-on collision, which is a kind of complex toy model, we can fit really well this signal. And I think it's really there is this synergy between numerical relativity, between the study of exotic compact objects, obtaining modeling gravitational waveforms, also real gravitational wave detections, and data analysis. So there is this synergy that lead to this result. And actually we manage, now if we assume that the Proca interpretation is, the Proca hypothesis is true, just has a proof of concept, then we can measure, we can estimate the mass of the particle, or the bosonic, ultralight bosonic particle, that we find to be around 9 times 10 to the minus 13 electron volts. So there is this really, I think, a really nice result that combines numerical relativity, gravitational wave observation, data analysis, and now particle physics. And maybe in the stellar graveyard, we have here GW190521 has the merger of 2 black holes in the Bayesian gap, but maybe could be that it's actually the mergers of 2 boson stars. And very quickly, let me say that, so we have started to do some, departing from head-on collisions, but to something which is an eccentric collision, so has an extra angular momentum. So the final hypermassive spinning Proca star takes longer to collapse, but at the end it does. But it will emit this longer gravitational waveform. So even if a head-on collision, because it's a short signal, we cannot really distinguish it from a black hole merger. But this signal, I'm not sure if it could be a black hole collision could emit this type of signal. So if we can detect, if LIGO-Virgo and Cara can detect this type of signal, we could then claim that we are detecting Proca stars, or at least a similar exotic compact object. Okay, to conclude, gravitational waves from bosonic star binaries could be used to detect ultralight boson particles. So we have done it for GW190521, but there might be others. So we will look for other gravitational wave events. So maybe it is time to rock and roll, or even to play the pentatonic scala. So thank you very much.
Very nice. Okay, thanks again. So very nice talk. Time for questions, guys. So if you want to use the button, raise hand, or just unmute yourself, go ahead.
I have a question.
Yes.
So first of all, congratulations for all the presentation and the Starway to Heaven at the end. I really enjoyed it. No, I would like to know if there are, because so this seems to be a way to put constraints on the mass of a putative Proca field, like massive complex. Like, are you aware if there are other ways to set these constraints? Because as I understand from the presentation you gave, like you cannot use super radiant instability to like for the real case. So are there ways to set constraints on the mass of the Proca field other than gravitational wave astronomy?
Yes. So actually there are constraints on ultralight bosonic particles, but so there is a debate, and I think those constraints only apply at least directly to real fields, because so these constraints are obtained following two measurements. So first, they are searches of this. So if you have this super instability for a real field, and at the end when you form the cloud, then this cloud decays emitting gravitational waves, which are monochromatic and continuous waves. So you can look for, using LIGO and Virgo data, you can look for trying to find this continuous and monochromatic wave in the data. And they cannot find anything. So it's a way to put constraints on the mass of the real bosonic particle. Then there is another way, it's to measure the spin of astrophysical black holes. Because so the super instability, actually there is a transfer of angular momentum from the black hole to the bosonic field. So there is a spinning down of the black hole. So if you measure, if there is a bosonic field, then it should trigger the super instability in astrophysical black holes, and the spin of the astrophysical black holes should be low. But actually, there's measurements of spins of black holes that are really high, like 0.9, 0.8. That is not compatible with the existence of a bosonic field. But again, I think those constraints only apply, at least directly, to real fields, because if you have a heady black hole which is stationary, actually there's a transfer of the angular momentum from the black hole to the complex field, but the complex field stays there. So there is no emission of angular momentum. The system keeps the total angular momentum. In the real case, it is not. You spin down the black hole, and then the angular momentum is radiated away through gravitational waves. But not in a complex case. In a complex case, the system retains the whole angular momentum. So my opinion is that those constraints cannot really be applied to complex field. We have to study really, for example, the accuracy, the way that the spin is measured for Kerr black holes, for like only Kerr black holes to measure the spin. We should repeat those studies, but for Kerr black holes with bosonic hair, to really see that there is a difference, and claim that those constraints can apply to complex bosonic field.
Okay, thank you very much.
Thank you
for the question.
More questions?
Hi, I may have a couple of questions. So first of all, thank you for the very nice talk.
Thank you.
The whole talk was nice, but especially in the conclusion, I guess. You mentioned that, at least from your work, you can conclude not that there is a strong evidence for the existence of Proca stars, but at least you can say there could be a degeneracy in interpreting in the data analysis.
Mm-hmm.
A way to break this degeneracy, did you think about it? Meaning that, as you already mentioned, when you have in spiral, the signal will be probably very, very different, and only the head-on collision of Proca stars could possibly be degenerate with a black hole merger.
Mm-hmm.
But for example, in the ring down, Could there be differences in the rig down, for example, detectable once higher overtones are detectable?
Yes. I mean, this is a Bayesian analysis, so at the end is what you get. So, for example, in head-on collisions, so for quasi-circular binaries, it's actually the L equal M equal 2 mode that dominates. But in head-on collisions, you also have the L equal 2 M equal 0 mode that is mostly important. It's also important. So you need this mode to really fit this signal. It's not so you need, but you cannot really distinguish between both scenarios. So can you break the degeneracy? Well, maybe. So we have started with head-on collisions. Maybe we start with like eccentric mergers. Maybe you get a solution that fit a little bit better the signal, but I don't really expect that because the signal is so short that if you get like the final parameters of the black hole, the mass and the spin, then you will fit quite well the signal. To really claim the existence of these Proca fields or exotic compact objects like bosonic stars, I would expect that we really have to detect this kind of signal that cannot be produced by a black hole merger or a neutron star merger.
Right.
But yeah, I don't think that we can really break to get, because if not, then the analysis of the LBC, that there would be, if you fit it with a binary black hole merger, then it would be residuals in the signal when you subtract the signal to the data, you see. And that will raise the alarms in the collaboration. So you can really fit the signal with a binary black hole merger. It's just that with a head-on collision of spinning Proca stars, you can also fit the data and slightly better.
Okay. Can I ask another question? A quick clarification, actually, that I like to ask you. So you were mentioning the stability of rotating boson stars and Proca stars before, with especially in the presence of a self-interaction for this boson or vector field.
Yes.
I mean, you found that for some parameters, yeah, exactly this picture. Thank you. The last row of results for very high coupling lambda, you saw that at least the configuration was kind of long-lived. I wanted to ask you a bit more on the timescales of your simulations. In milliseconds, what would that timescale be?
Okay, so actually this you have the particle mass, which is the scale of the problem. It's not the mass of the star, it's the
right.
So if you want like that this star has one solar mass, so the mass is around 10 to the minus 10 electron volts. Okay, so this would be so you have to multiply around by times 10 to the minus 6. So this would be like 20 milliseconds, I think, around 20 or 50. But if you go to even lower masses of the particle mass, so for mu 10 to the minus 10 electron volts, this would be 20 milliseconds. But if you go like to 10 to the minus 15 to 10 to the minus 19, sorry. So these time scales are much longer. So in this case, it would be like 5 orders of magnitude or even 9 orders of magnitude that time.
Okay, so it could be arbitrary long depending on the mass of the particle.
Yeah. The thing. So we could define this kind of stability as it's a transient, but it's really long, at least for a dynamical time scale. So it's like an effective stability. So the object is not stable in the complex sense of the word, but it's stable for a long time. But then Simonsen and East show that really for some values of this lambda and for other couplings, then the stars are really stable. It's not that the instability takes a lot of time to appear. They are really stable, or at least that's what they conclude.
Okay, thank you.
Thank you.
Thanks, Ale. I think we have one more, Jason.
Yeah. Hi. It
Hi.
was a nice talk. Thank you very much. I enjoyed it a lot.
Thank you.
Are there alternatives other than the merger of two black holes or the collision of two Proca stars to explain the gravitational wave event of 2019?
That I know, no. So, I mean, people might have different theories, but that you really use numerical relativity to build this gravitational catalog of your model, and then you compare using data analysis to the real gravitational signal. No, that I know. So for example, now there's a lot of discussion about GW190521 that instead of being this quasi-circular merger of precessing black holes, it could be an eccentric collision. An eccentric collision, not a head-on collision, not that extreme, but really with high eccentricity. And actually, there's a lot of people now try to develop numerical waveforms and numerical surrogates of eccentric mergers, of highly eccentric mergers, to see if it could be fitted by, so if we could fit this signal with those models. But it's always a black hole.
Okay, thank you.
Thank you.
Okay, more. I think Alexander has more.
If somebody else has questions, they can go ahead. I just remembered I have another question. Sorry.
No, go ahead. Go ahead. I don't know. Nico, are you in a hurry?
No.
Okay.
Okay, thank you. You were mentioning that you had studied the formation of black holes with synchronized hair as a byproduct of the merger of two boson stars or Proca stars.
Yes.
And however, you found that there's a fine-tuning required in order to achieve the synchronization criterion.
Yes.
Condition, sorry. Can this happen also as a byproduct of the collapse of a Proca star or boson star?
So of a spinning boson star. So we tried to. So it was actually Miguel Silao who was doing the collapse of the spinning scalar boson stars, and we tried to get the precise model that when collapsing it would have the right spin and the right oscillation frequency. The thing is that so when the scalar boson star collapses, so for really compact models, we were getting an m=3. But then when we were getting close to the correct value of the spin, it changed to an m=1 or m=2, I don't remember. So we were getting to the, we were having the correct horizon velocity, but then the m decreased. So we couldn't really find that synchronization condition in the collapse of a spinning scalar boson star. But actually, this comes from the head-on collision of two excited m=2 Proca stars. Spinning, I mean, of course. So I've said that the mergers of two non-spinning bosonic stars can form these hairy black holes, but also the head-on collision of two spinning bosonic stars can also form these hairy black holes. But the collapse, we couldn't find, at least with the mini boson stars. Maybe with a self-interaction potential could lead to the synchronization condition.
Okay, thank you.
Okay. Yeah, it was 20 something, but it's not a very big deal. So did you say something that you are working in the initial data?
Yes.
Because your template are in head-on collision, no? So what are the technique that you use? I know, I want to gossip about this one. Are you working in the initial data for Proca boson star in quasi-circular orbit?
Yes, yes.
Oh,
Also,
okay.
the thing is that, yeah, so in numerical relativity, so, well, you know it very well, but what we do to do these mergers is we take two boson stars, the solution of the boson stars, and we do a superposition of the space-time and of the fields. The thing is that we have to then solve the constraints to get the solution of that superposition. If not, it's violating the Einstein equation. It's not a solution of the Einstein equation. So the thing is that head-on collisions are less, the constraint violations are smaller than a boosted solution, an orbital merger. So we started doing head-on collisions, and now we are trying. So yeah, we are trying to obtain the initial data.
Okay, nice.
Or,
So
or
and are you planning to do like a Lorraine for initial data for boson star, and we can download your initial data from
yeah,
somewhere?
that would be really great. But yeah, that's like a long
Yeah,
term.
yeah, yeah. Okay. Thanks, Nico. Very nice talk. Thanks
Very much.
for all of you being here.